Welcome to 4.2. We're going to carry on from what we learned in 4.1, which was basically how are we going to relate two values to each other. We started with plots and then looked at boards. So how were plots related to the number of boards he needed? We looked at planes, the distance, the height of the plane, and how long they'd been descending. So time was somehow related to the height of the plane. So we looked at cab rides. How was the distance of a cab ride related to the cost? So we're going to continue on with these relations, relating two numbers together, and keep working on our patterns and building expressions from patterns. So here we've got a drawing. Okay, so the first four rectangles in a pattern are shown. The pattern continues. Each small square has a side length of 1 centimeter. Okay, so the perimeter of the rectangle is related. Okay, so there's a couple key words there. The perimeter is related to the rectangle number. Okay, so the rectangle number, okay, for instance, is rectangle 1, right? It's these ones right here. The perimeter is around the outside. Okay? So we can use words, a table, a graph, and an equation to represent this relationship. In words, okay, so rectangle 1 has a perimeter of 6 centimeters. Is that true? 1, 2, 3, 4, 5, 6. Correct. Okay, so if rectangle 1 has a perimeter of 6 centimeters, then the rectangle number increases by 1, its perimeter increases by 2. So instead of rectangle 1, which we said is 6, let's look at rectangle 2. Now it's 1, 2, 3, 4, 5, 6, 7, 8. Okay, is rectangle 3 going to be 10? Because that would be a nice pattern, wouldn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and I think we can just assume that this one's going to be 12. So there's a nice pattern where it jumps up by 2 centimeters every time that you extend this out. So really, you can see what's happening. When you go from here to here, all that's happening is they've taken this piece, moved it over, and added the two pieces on the top and bottom. So that's why we're getting a +2 every time. They add these two pieces every time. So, pictorially, the picture makes sense, and it looks like the numbers make sense. So how are we just going to, take all this information and make a nice general math statement where we can get maybe rectangle 431 without having to draw 431 rectangles? Okay, so we did the words. Okay, so the rectangle number increases by 1, perimeter increases by 2. So that's the relationship. You can see the rectangle number, so rectangle 1, 2, 3, 4, it's just going up by 1 each time. 1, 2, 3, 4. And here is the other important part. The perimeter is going up by 2 each time. So remember when I said that when you're building your expression or equation, this number here usually needs to be multiplied by this number here. So look at what we've got for a perimeter expression or equation here. 6 equals 2 times 1 plus 4. Now, where did we get the 4 from? Okay, where did we get the 4 from? So this is where we got the 4. No matter what, okay, no matter what, and if you're going to make a square, you're going to need 4 sides. Okay? Let's just say we had rectangle, let's just say we had a different rectangle over here and called it rectangle 0. Okay. Well, the next pattern going this way would be something that looks like this, wouldn't it? Right? Because this would have to just go there, and we'd get rid of those 2. And how many sides do we have there? 4. So that's where the 4 comes from, is we need to have a minimum of 4 sides in order to close a square or a rectangle off. So we know we need to have 4. So that's where the 4 comes from. How many more do we need? Well, our picture and this consistent jump, tells us that it needs to be 2 times whichever rectangle number they are. All right, so let's just add in rectangle 0 to this chart, right? So if we had rectangle 0 on one side, okay, the perimeter equation still works, okay, because we would have the perimeter is equal to 2 times n, which is 0 in this case, plus 4. Right? N is the rectangle number, and I just said, let's pretend we've got rectangle 0 here. So if n is the rectangle number, which is 0, I don't know why I put the 0 there. I should have said this is the rectangle number. Okay. So if the rectangle number is 0, okay, what is the perimeter? Well, 2 times 0 is 0, okay, plus 4 equals 4. So it works. So if we did have rectangle 0 up here, it would work fine. What about if we had rectangle number 5? Well, rectangle number 5, the same equation holds. Okay, so we've still got the 2 times the n, which in this case is going to be 5, right? The n is always going to be whatever number is in this column, plus the 4. So that would equal, oops, I got the equals up top there. That's 2 times 5 is 10, plus 4 is 14. So if we were to draw another rectangle on the other side here, it's going to be rough, but if we were to draw another rectangle, we've already got 1, 2, 3, 4, 5. I've already got 5 rectangles here in this last one. So it's 1, 2, 3, 4, 5. So I just drew this one again. But what happens if I want to extend it? I've got to add one there, and one on the end. So I have to add this one and this one. And still got the end piece. So how many do I have in total here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It checks out. Remember, I don't have to have barriers in the middle. I'm just doing perimeter, so I just care about what's on the outside. So I'm not counting these ones in the middle. The point is, I set rectangle 0, and it worked. I set up a rectangle 5, which I should probably note down here, rectangle 5, and it still worked. Okay. So now I can figure out rectangle 443 if I want, and I don't have to draw 443 of these things in order to figure it out. A graph can also show patterns, okay, and it allows us to compare and find a relationship with two numbers. There's just numbers up here on the y-axis. Don't forget that. If we're looking at what's known as the Cartesian coordinate system or the plane coordinate system, y's are up and down, okay, x's are left and right. Okay, so y are up and down. Probably shouldn't use an arrow to denote that. And x are your values from left to right. We've got to keep that in mind. Okay, so this shows a pattern. After the first point, each point is 1 unit right and 2 units up. Well, let's test that. Here's point number 1, okay? And point number 1 is related to 1. It's not written on the graph, but if this is 2, this has to be 1, this has to be 3, this has to be 5. Okay? So if we look at 1, if we go over to the right 1 and 2 up, do we hit the next point? Over 1, up 2, we do. Okay, so this is true. Okay? So each point on the graph is 1 unit right and 2 units up from the one before it. If we put a ruler, we notice that this is a nice straight line. And a straight line on a graph like this indicates that there's a relationship, and it's a linear relationship. That's where the linear comes in. Okay, it's a line, right? If I can draw a line from this through all these points, okay, which I can. Didn't draw my line very perfectly, but I can cover all those points with one line. That means that it is a linear relationship. That's where the linear part comes in. This whole unit is called linear relations. Okay? We don't join the points because the data are discrete. Now, that's an important concept. Okay? The data is what we call, oh, good grief. The data is what we call discrete on this. Okay? So unless they specifically tell us, okay, data points between these, okay, we can only tell you what's happening at 1, at 2, at 3, and at 4. We can't make any assumptions about what's happening at 3.5. Okay? So essentially we know things about, let's say that's x, right? So x equals 1, 3, 5. Okay, so 1, 2, 3. Oh, I'm sorry, 1, 2, 3, 4. Doesn't skip. 2, 3, and 4, okay, we do not know anything about 1.5, 3.7, etc. Okay? So it's discrete, which means you just know at that point what's going on. You can't say anything about what's going on between numbers. All right, so looking at this in an equation, for any rectangle n, the perimeter is going to be 2n plus 4. Okay, where did that equation come from? I don't know. I think they just gave us a random one. So the equation tells us that we can calculate the perimeter of any rectangle in the pattern by multiplying the rectangle number by 2 and then adding 4. Oh, sorry, this relates to the question on the previous page, right? So this was the equation right here, which is basically the number n and the perimeter p. So the p was equal to 2 times n, which is the number of rectangles, plus 4. So that was an equation that we built and put in here. We just didn't use the p and the n. P equals 2n plus 4. So let's flick back to this page. P equals 2n plus 4. So that's where that equation came from, right? Expression. And then equation. The equation tells us we can calculate the perimeter of any rectangle by multiplying the rectangle number by 2 and then adding 4. That's just what this means. Okay, the value of the variable p depends, this is important, on the value of n. What that means is if the p is going to change based on the n. So if n goes up, the p has to go up too. If n goes down, the p has to go down. So the n depends on the value of n. So we say that p is the dependent variable. Okay? And that's always on the vertical axis, so that's on the y. Okay? The other variable is called the independent variable. And that's always going to be on the x. Okay? So if we look at this chart up here, okay, which is really just the equation that we made for the perimeters of the rectangle, just put on a graph instead of drawing a picture. If we look at this particular graph, okay, the dependent variable is on the vertical, and the independent variable is on the horizontal. So this n is the number of rectangles. So for rectangle 0, we had 4 sides. That was the perimeter. Not 4 sides, sorry, the perimeter was 4. For rectangle 1, it was 6. For rectangle 2, it was 8. For rectangle 3, it was 10. Rectangle 4, it was 12. And we also did rectangle 5, which was 14, which would be way up here, right? So this would be 14. So this graph just relates right back to this question that we did right here. Instead of drawing the picture or the table, we took all these data points and just put them on an XY graph. So see, 1 is 6, 2 is 8, 3 is 10, 4 is 12. Exact same thing here. 1 is 6, 2 is 8, 3 is 10, 4 is 12. And we added a couple extra data points just to check our stuff. Okay? When the two variables are related, okay, which they clearly are, you know, as the n goes up, p goes up by 2 more, right? 2 more, 2 more, 2 more, so it's consistent. So they're related. When two variables are related, we have a relation. Okay? A relation. And in this case, it's a linear relation. And you could tell a linear relation pretty easily because it is consistent in how much things change. Okay, has to be consistent. And then what that means is to be plotted on a chart, XY graph, these will all be in a perfectly straight line. if you see a relationship where you got dots kind of all over the place and they don't look like they're on a straight line, it's not a linear relationship. It's a relation, but it's not a linear relation. So when the graph of a relation is a straight line, we have a linear relation. In a linear relation, a constant change in one quantity produces a constant change in the other. So when we say constant change, if we look at this, the constant change would be if the n goes up by 1, and it goes up by 1 every time. That's constant, right? If the n goes up by 1, okay, the p is going to go up by 2. So n goes up by 1, p goes up by 2 every single time. So that's what it means by constant. It's a constant change in one produces a constant change in the other. In this case, constant change of +1 for the number of rectangle. Okay, that's +1 constant change, and the constant change in the other one, which was the perimeter, would be the +2. So in the relation above, a constant change of 1 in n produced a constant change of 2 centimeters in p. It's all related. All right, so here's another linear relation. Y equals 3x minus 5. Okay, x is the independent variable, so it's going to be plotted on the horizontal. Y is the dependent variable, so it's going to be plotted up and down. That's why x is across and y is up and down. Okay, so here's a table and a graph that represent an equation. If x is 0, okay, so here's 0, y is -5. There it is right there. There's the point. Okay, and I'll just put these data points on the chart as we work along here. So what's our next one? If x is 1, y is -2. Okay, so 1 for the x, and then -2 for the y. What are we here? X is 3. X is 3. Oh, no, sorry, x is 2, 1. Right there. 3, and then y is 4, and then 4, and y is 7. Okay, so this is clearly a linear relation because they're all in a straight line, right? And this equation produced this straight line because what happened here is if you give us the x, we give you the y, right? So on this side, it's really y equals 3x minus 5. Well, let's test it, okay? So if x equals 0, okay, then this one should be 3 times 0 minus 5. Does that equal -5? Yeah, it checks, okay? So let's do this one. So this one should be 3 times x. So if x is 1, minus 5, 3 times 1 is 3, minus 5 is -2. It checks out, and you're going to find it checks out the whole way through. Okay, so this is going to be 6 minus 5 is 1. Okay, this one's going to be 3 times 3 minus 5 is going to be 9, minus 5 is 4. And this last one's going to be 3 times 4 minus 5. So that's 12 minus 5 is 7. So all of those checked out with this equation. So when you see an x and you see a y on this side, it really is just telling you y equals, you know, this part of the equation, the expression. So our constants here is every time x moves up by 1, y goes down by 5. Okay? So if x goes up by 1, so here's x going up by 1, y is going, here's x going up by 1, y is going up by 5. Oh, yeah, sorry. This is up by 3. What are we doing here? Oh, sorry, I didn't want to confuse the issue. I wrote these over top of the pattern, and that was probably a bad idea. Okay. So I'll erase it. What I wrote there was absolutely true, but I didn't want to cover up this. Sorry, when I was talking about the constant, okay, so constant increase of 1 on this side. And then over here, it's a constant increase of 3. So they're both constant increases, right? But in reality, what I had before is absolutely right? The y on this side is equal to the equation we had up there, which was 3 times x minus 5. I had the minus 5 in my head for some reason instead of the plus 3. But we can see that this is true, right? Each time that y goes up by, or x goes up by 1, so here x is 1. If x goes to 2, y is going up 3, right? 1, 2, 3. If x goes up another 1, y goes up another 3. 1, 2, 3. 1 over 3 up. 1 over 3 up. All the way. And it'll go on forever, right? It also goes on forever this way, too. So when x increases by 1, y increases by 3. It's shown on the table. It's shown on the graph. Since they're on a straight line, the equation y equals 3x plus 5 is a linear relation, right? Just a line that covers all those points perfectly, a straight line. Since we are not told the data are discrete, So basically you have to be told the data is discrete. So you have to be told that there is something in between these 2 points. Otherwise, you just put them as dots. Now, I didn't do a great job of explaining that before. Let me explain why the data on this previous chart is discrete. Now, this is the one where we're talking about the perimeter of the rectangle, right? So it's basically how many of these boards do we need to cover the outside of each of these rectangles. Well, if you think about it, rectangle 1's got 6, rectangle 2's got 8, rectangle 3's got 10. What about rectangle 3.5? Is there any way we can draw a rectangle 3.5 that has 9 boards that makes a perimeter? Is there? Well, not really, because we've got these boards that are this long. How are we going to draw a rectangle 2.5? There isn't one, or 3.5, or 3.1, or 3.2. There isn't one. It goes straight from rectangle 1 all the way to rectangle 2. So you either have 6 boards for 1, or 8 for 2, or 10 for 3, or 12 for 4, and so on. But there's no such thing as rectangle 2.5, or rectangle 3.1. Okay? Which means that these are just points on a graph, and we don't join them because there's nothing in between here. There's no way to make rectangle 1.2. That's why these are just dots and not actually joined. So the same thing for this one. It didn't tell us that there was anything in between here, so we can't join these dots. This line right here was just the one that I drew over top, just to represent that they are in a straight line, but we can't join the dots. All right, so here's a practice or skills example. Construct a table of values for each relation. Use 2 negative values, 2 positive values, and a 0. Graph each line on a coordinate plane. So this is all you need to draw a table, and here's how it works every single time. Okay, so on one side, you're going to have the x, on the other side you're going to have the y. Okay, now traditionally the x is over here and the y is over here, and you don't just write y up here, you write the whole equation. Okay, because this y is the dependent variable. Okay, so you're going to have the independent variable on this side, the dependent variable on this side, and you're basically going to write the equation again, so negative 2x. So it says, let's use 2 negative values, 2 positive values, and a 0. Here's how you do it every time when I'm asking for these values. There's our 2 negative values, there's our 0, and there's our 1. So it's easy for us to tell our pattern. Why did I put them in that order? Well, because it's just a consistent +1, +1, right? +1, and +1. It would be silly if I wrote -2, 2, 0, 1, -1 in no order, right? You want to make it so that both sides have a pattern. Okay, now let's solve for the other side. Because we've got an equation, that's all we need. So y equals -2x. So y here is going to be equal to -2 times the x. Well, the x is -2. So y is going to be -2 times -2 is +4. In this one, y equals -2 times the x, which is -1. So -2 times -1 is -2. This one, y equals -2 times 0. Anything times 0 is 0. Okay, so look at the pattern. We're going from 4 to, why did I write -2? That should be +2, sorry. Yoink. We went from 4 to 2, and then from 2 to 0. Hopefully you're noticing a pattern starting to evolve here. Y equals -2 times 1 equals 2. Well, what's the pattern? How do we get from 4 to 2? It's -2. How do we get from 2 to 0? It's -2. How do we get from, this is negative. How do we get from 0 to -2? It's -2. And then for our last one, well, we know it's going to be 4, right? Because it's going to be negative 2 times positive 2 equals negative 4. So our pattern holds the whole way through, which means that this is a linear relation. Okay? So let's plot those data points over here, and let's see what it looks like on a graph. And these dots should all be in a straight line. Now, you have to have consistent spacing between your elements. So I'm going to look at all the numbers I have. I go from positive 4 to negative 4, so that's 8. So 1, 2, 3, 4. So I'm going to say every two of these squares is going to be equal to, okay, every two of these squares is going to be equal to 1. So when I make up my chart here for my x and y values, I'm going to say that's 1, and then 1, 2, and then that's 3, and then that's 4. Okay, so every 2 blocks is equal to 1, and then same thing on the negative side. It has to be consistent. Negative 1, negative 2, negative 3, negative 4. You can't go, skip a block. You can't go, 1, 2, and then make the 3 in the middle here. You always have to have the same distance between them. Okay. And then what do I need for my positives? We'll do the same thing. So this will be positive 1, positive 2, positive 3, positive 4. And then over here, this will be negative 1, negative 2, negative 3, and negative 4 is right there. All right, now let's plot our values. For x value of negative 2, our y value is 4. So here's our x, negative 2, and it's going to be positive 4. So let's go up to the positive 4, which is right there, right? So found the negative 2, and then I went up to there. Next one is negative 1, and the y value is 2. So negative 1, y value is all the way up to 2, right? Negative 1, and then up to 2. Then we got 0 and negative 2. So we've got 0 and then negative 2. I feel like I made a mistake here. 2 times 0. Just going to check max wise. 2, 4, 2. X is 0. Oh, sorry. I did make a mistake. But it was on the graph, not on the data. For some reason, I said 0 is with negative 2. I went too far. 0 is 0, right? So 0x is 0y. 1x is negative 2. So 1x is negative 2. Okay, and 2x means a y of negative 4. So 2x means a y of negative 4. Okay, now it's pretty clear to see, even though that's a reasonably sloppy graph, if I were to put a line, that goes through all these points, all of those lines are on the point, which means that's a linear relation. I knew that already because we already determined, get rid of that line. We already determined that this was constant and this was constant. So if they're both constant, for every increase of 1, we get a decrease of 2. We know it's just by definition that it's a linear relation, but we also kind of proved it when we put them on we plotted them on the chart, and they all were in a perfect line. Again, they didn't tell us that there was anything between these points, which means we have to assume they're discrete, which means you just put the dots. You don't actually join these things together. Okay, let's do it again. This one I'll do quicker because it's, the exact same process that we had before. All right. Maybe I'll draw on a different color this time. That might make things easier. Okay, so we've got our x values on one side, and then we've got our y values, which are equal to 3x minus 4 on the other. So let's start with negative 2, just like we did before, negative 1, 0, 1, and 2. All right, so if x is negative 2, y equals 3 times x minus 4. So 3 times negative 2 is negative 6, minus 4 equals negative 10. All right, this one, y equals, same thing, 3 times, except x is negative 1 this time, minus 4. 3 times negative 1 is negative 3, minus 4 is negative 7. Hopefully you can see the pattern already. So y equals 3 times x is 0 this time, minus 4 3 times 0 is 0, minus 4 is negative 4, and you're noticing the pattern, right? So I don't think I even have to do the rest of these. You know that it's going to go down by, or up by 3 every time, right? So plus 3 to negative 7, plus 3 to negative 4, that'll be negative 1, and the last one's going to be positive 2. So our consistent jump is plus 3. Our constant for this side of the table is going to be adding 3 every time. What's our constant on this side? We're adding 1 every time. Right? So we know this is a linear relation just because we've got a consistent increase or decrease, doesn't matter. We've got a consistent change here and a consistent change here, which means that when I put it on the graph, I know it's going to work out. Now my graph goes to negative 10 this time, so I'm going to have to space things out a little differently. Your x spacing does not have to match your y spacing, but everything on the x has to be the same distance apart. And so I'll show you what that means. I've only got 5 values for x, and they only go to negative 2, so I can make 1, 2, 3, 4. I'll make a 4 boxes equal 1 unit. Okay, so each 4 boxes on just x, we're just talking about x here. 1, 2, 3, 4, so that would be negative 1. 1, 2, 3, 4, so this would be negative 2. And then same thing on the other side. 1, 2, 3, 4, this would be positive 1. 1, 2, 3, 4, this would be positive 2. So the distance between these has to be consistent, but I do not have to do the same thing on the y. I can do a different set of spacing on the y as long as it's consistent. So for the y, I have to go all the way down to negative 10. So I'll maybe make just each one of these 1. So the first 1, this would be 2. This would be 4, 5, 6, 7, 8, 9, 10's at the very top. So same thing on the bottom. Minus 2, minus. I'm just skipping between because there isn't enough room for me to write all of them. So my scale is different. You know, there's this much space between 1 on the x, and there's only this much space between 1 on the y. That's okay. They don't have to match, but they do have to be consistent. Okay, so let me just pick a different color here, maybe, for making my points. If x is negative 2, well, there's negative 2. Y is negative 10, so that's all the way at the bottom here. That's our 1 point. Our next point is negative 1 should be negative 7. So negative 1, we've got to find negative 7. So this is 4, 6. Between 6 and 8 is going to be 7. So where's my negative 1? Right there. Right? 1, 2, 3, 4. So that's negative 1. And then 1, 2, 3, 4, 5, 6, 7. Perfect. 0 is going to be negative 4. So x0 is going to be negative 4, which is right there. X1 is going to be negative 1, so x1 here is going to be negative 1 there. And then x2 is going to be positive 2, so x2, the y is going to be positive 2. There we go. So I've plotted the points, and it should be easy to see that, even though it's a bit sloppy, if I draw a straight line, it should go through each one of those points, you know, perfectly. I didn't draw the thing perfectly, but that is definitely a linear relationship. And we already knew it was a linear relationship, because remember, as soon as you build a table, that you've got consistent increases or decreases on one side and consistent increases or decreases on the other, we know that it's a linear relation, and we know that if we plot it on a graph like we did here, we know it's going to end up being a straight line. All right, here's one more. A relationship has an equation of y equals 6 minus 3x. Create a table of values from negative 3 to 3. Graph the relation. Does it make sense to join the points on the graph? Okay, well, I don't know. So let's draw a table. X on this side, y on this side. Yoink, yoink. So we've got, it says from negative 3 to 3. So negative 3, negative 2, negative 1, 0, 1, 2, 3. So that's how many points we're going to have. Y is going to be equal to 6 minus 3x. Now, you don't always have to do the equation in here. I'm just doing it right now to make sure you understand how we get the y values. So maybe I'll do it for this one and not for the rest. So we find out our y values. Our y values are going to be 6 minus 3 times x. So the x is negative 3, right? So that's going to be, what's 3 times negative 3 is negative 9, so 6 minus negative 9, so that's really going to be a plus, right? Right, we could look at this. We could look at this a different way. We could look at this as negative 3 times negative 3 is a positive, right? Or you can look at it as 6 minus, and then what's 3 times negative 3 is negative 9, right? So you could look at this like this, right? But isn't it easier just to say plus equals 15, right? So what's the next one? Next one is going to be 6 minus, I'll do it for this one too, 6 minus 3 times negative 2. So that's going to be 6 plus 6 equals 12, okay? The next one, y equals 6 minus 3 times negative 1 equals 6 plus 3 equals 9. You can already see what's happening here, right? Minus 3, minus 3. You know what's going to happen for the rest too. Okay, so minus 3, minus 3. So if this is 9, this one's going to be 6, 3, 0, negative 3. Okay, now it's acceptable just to write the values in y. Just make sure you're right, okay? Test a couple of them. I don't expect you to write this out for each one of your y values, but I'm showing you how I got the numbers. So 15, 12, 9, 6, 3, 0, negative 3. I just filled out these because I knew what the pattern was. What's the pattern over here? Plus 1, plus 1, plus 1. The whole time, right? Okay, so let's graph it. Our y values go up to 15, so I might have to do a little work here because I think there only goes 10 up. Y values go to 15, x's only go to 3. So I'm going to pick a different color here. First I'll draw my scale. So I'm going to say that each one of these things is 2. So this is going to be, it's going to get a little cramped here, but this is going to be, draw slightly here over here. So this is going to be 2, okay, 4, 6, 8, 10, 12, 14, 16, 18. Okay, and I'm only drawing every second one because 2, 4, 6, yeah, okay, so negative 2, 4, negative 6, negative, negative 6, negative 10, negative 14, just because I need to get down to up to 15 for one of my answers. 15, 14, 18. Okay, now for the x's, because I don't have to go nearly as high, maybe I'll do each, maybe I'll do that thing again where I had, I'll do 3. So 1, 2, 3, that'll be negative 1, 1, 2, 3, that'll be negative 2, 1, 2, 3, that'll be negative 3. So each 3 blocks is worth 1. So 1, 2, 3, 1, 2, 3, 1, 2, 3. There we go. Now I'll switch colors and let's just plot the points. If x is negative 3, okay, that's all the way over here, y is positive 15. Okay, so this is 14, this is 16, so 15 would be actually in the middle of these two, so I have to make a point right in the middle. Alright, so if x is negative 2, y is 12. So if x is negative 2, y is 12. 10, 12. Okay, so negative 2 and 12. And then it's negative 1 and 9. Okay, so here's negative 1. That's 6, 8, 10. So it's going to be, again, it's going to be right between this one, which is 8, and this one, which is 10. So 9's right in the middle. 0 and 6, so 0 and 6. Okay, now you already see it's linear, right? 1 and 3, so 1, that's 2, that's 4, so 3 is going to be right there in the middle. 2 and 0, that one's easy, right? X equals 2, y equals 0. And then 3 and negative 3 is going to be right there. Now, I'm not going to do it, but, if I drew my line over top, it looks like this is a nice straight line and all the dots will fit on the line. So it is linear. Okay, is the relation linear? Justify your answer. Well, okay, there's one justification right there. It's a straight line. Okay, a second justification. Let's see, we did A, B. Does it make sense to drawing? Okay, let's look at Let's look at B, okay, before we get to D. Graph the relation. Okay, I did it. Does it make sense to join the points on the graph? Explain. No. We do not know what the data represents. And the data are just the numbers, right? So we have to assume it is discrete. Discrete meaning we just put the dots. Okay, they didn't give us enough information anywhere in here for us to tell, is there a negative 2.5? Is there a negative 2.7? We don't know that. We don't know what these numbers are dealing with. Are we dealing with, the number of, are we dealing with an airplane question where it's height and then the x is distance or time? Are we dealing with a cab question? Are we dealing with a garden question or something else? We don't know. They didn't give us enough information. So if they don't tell you, okay, that it's not discrete, you just have to assume it is discrete. They have to specifically tell you that there are points between these in order for you to join them with a line. C, what patterns are in the graph? How do they relate to the table? Okay, well, let's just look at the graph. What happens, when we start at negative 3, how do we get from here to here? Okay, we are going over how many? 1, and then we go down 3. So this is over from negative 3 to negative 2, so that's plus 1. And then from, 15 to 12 is minus 3. And we're not talking about the number of boxes. We're talking about the number of units, right? From negative 3 to negative 2, that's 1. That's plus 1. From 15 to 12, so from 15 to 12 is minus 3. So what's happening? And how does it relate to the pattern? Same thing, right? Every plus 1 equals negative 3. Every plus 1 equals negative 3. And any 2 points are like that, right? If we start here and our x changes by plus 1, our y changes by negative 3 the whole way down. So for every unit we move right on the x-axis, we move down 3 on the y-axis. And that matches up. That's just the words version of this. For every every time we increase x by 1, we decrease y by 3. So for every unit we move right, and then I should put above this, that's plus 1, on the x-axis, we're moving down 3 on the y-axis. So that's how the chart relates to the table. And then D, what did it ask us for D? For D, it says, is the relation linear? Justify your answer. Okay, yes. Okay, there is constant change in the table for both the x and y values. Okay, so the x would be the plus 1, right? And the y is the minus 3. Because it's constant change on both sides, we know that it's a linear relation. What's another way we know? Also, the pattern of plus 1 minus 3, which is really over 1 down 3, over 1 down 3, of over 1 down 3. Well, I shouldn't say over 1 because it only applies when you're going to the right. So the pattern of right 1 down 3 is evident on the graph. Okay, so that's another way you could justify that that's a linear relation. A third way is you can make a straight line through all the points, okay, on the graph. Also, if you need a third reason, you could draw straight line, over all of the points on the graph. That's another way you can tell that it's a linear relation. So we basically got 3 justifications for that being a linear relation. We don't always see equations where y is isolated. Isolated just means by itself on one side, right? Sometimes we need to isolate it before we construct our table of values, right? So let's review those 2 steps. Okay, 1, get variable on one side. Okay. Get the variable on one side. Okay. Alone. 2, okay, divide out the number in front. And sometimes there is one and sometimes there isn't. So just keeping those 2 steps in mind, we should be able to solve these pretty quickly. I'll move back from the black. And isolate y. Okay, well, number 1, get the variable on one side alone. So I want to keep the y here, and usually I want to keep it positive too. So what do I need to do to get the y alone? Because currently there's a 6 there. Plus 6, how do I get rid of a plus 6? I subtract 6. Whatever I do to one side, I must do to the other. So now, 6 minus 6 equals 0. That got rid of it. Okay. And then on the other side, 4 minus 6 equals negative 2. Okay. I didn't need to divide out the number in front because there was no number in front of the y. All right, same thing over here. Now I've got a y and an x, but I only care about the y. Okay. In this case, we care about the y. If we cared about the x, we'd just make sure the x was alone. So how are we going to get the y alone? Well, we're going to leave it where it is because it's positive. How do I get rid of an x? Well, I subtract an x. And how do I get rid of an x? On one side, I have to do the exact same thing on the other. So if I go x minus x, that's just 0. So I can get rid of it. And then over here, I've got minus 2 minus x. I can't go any further than that because I don't know what x is. All I want to do is figure out what y equals. Okay, same thing here. Now I've got 2x minus y equals 6. I need to get the y because I only care about the y. It says isolate y. It doesn't say anything about x. I need to get the y alone, and I need it to be positive. Okay? So if I'm going to make y positive, it can't stay on this side. It's a negative on this side. I got to get it to the other side. So what I'm going to do this time is I'm going to add y to this side, add y to this side. So there's going to be 2 steps. So if I add y to the left side, negative y plus positive y just cancels out. And then on the other side, I've got 6 plus y. Okay, well that didn't get us all the way because we got a variable on one side, but we need it to be alone. Well, currently there's a 6 over here, so let's get rid of the 6 by subtracting it from both sides. Okay? So now we're left with, on this side, 2x minus 6 equals, well, 6 minus 6 is 0, plus y is just y. Okay? Now, it doesn't matter. It doesn't matter which side. It doesn't matter which side the y is on, as long as it's positive. This is the same, okay? It's the same as, I don't know why I circled it like that, that was silly. Okay, so 2x minus 6 equals y is the exact same as y equals 2x minus 6. As long as you don't change any of the signs or the order, it's the same, okay? So, same. So just because you have it written backwards as something equals y, or y equals something, they're exactly the same thing. So you can leave it like this if you want, or you can swap it around to this. I usually swap it around just because I like to have the dependent variable, the thing I'm solving for, on the left side. Okay? It's not wrong if you leave it this way, but it's kind of more common in math to write it like that. All right, now let's, again, we didn't have to divide anything because there was nothing in front of the y. There was something in front of the x, but there was nothing in front of the y. This time, we are going to have to do step 2. So let's get the variable alone on one side. It's not alone right now. There is an x. When I say alone, it doesn't include the number that's multiplied by y. It just includes addition, subtraction, that sort of thing. Okay, so let's get it alone. in order to get it alone, we got to get rid of this negative x. So how are we going to do it? We have to add x. Okay? If we're subtracting, we got to add to get rid of it. Whatever we do to one side, we have to do to the other. So we're left with 3y over here. This just cancels out. And then on the other side, we're left with 9 plus x. Okay, now normally we'd be done. In the other 3 questions, we were done. But now we've got a 3 in front of the y, right? So it's 3 times y. All right? So we have to take care of that 3. Well, what do? We divide out the number in front. Again, there's a special name for this, but we're not there yet. So we need to divide out a 3 from one side, which means we have to divide out a 3 on the other side. So over here, the 3's cancel, and we're just left with 1. So 3 divided by 3 is 1 times y. Well, 1 times y is just y. That was the whole point of this. And then on the other side, we've got 9 plus x over 3, which you can write as 9 plus x over 3, but I would prefer you write it as 9 over 3 plus x over 3. Why? I just think it's a little easier for you to recognize that 9 divided by 3 can be simplified, okay, to 3 plus x over 3. If you prefer to write it this way, that's a-okay. Sometimes people forget they would do 9 over 3 plus x, forgetting that everything on this side needs to be divided by 3. So if this is the way you prefer to go, and then you just cancel like this, and end up with 3 plus x over 3, that's okay, but I kind of prefer this version right down here. Anyway, we had to do more than one step for this one, and we ended up with y equals 3 plus x over 3. Had to do a little division there. Graph the linear relation in part C. Oh, okay, so they're going to pick the toughest one, of course. A, B, B, C. Well, that's silly. That should be C right here. Let's just change this so that this is C, and change this so this is D, because I think that's what it was supposed to be. Okay, so we're going to graph this one down here. Easier to graph than using a fraction, that's why I picked it. So if we're graphing a linear relationship, let's separate out into our x's and our y's. Sorry, put my y on the wrong side. So this is going to be our x, and this is going to be our y. And what is our y equal to? 2x minus 6. Okay. So I am going to do my usual, start at -2, and then go up by 1 until I hit +2. Always a good idea to have some negative values, a 0, and some positive values when you're graphing. Okay, so y equals 2x minus 6. Okay, so I'm not going to put the math here anymore. I'm just going to tell you how I'm doing it. X equals -2, right? So 2 times -2 is -4, minus 6 is -10. Okay, now x is -1. So 2 times -1 is -2, minus 6 is -8. Okay, for 0, 2 times 0 is 0, minus 6 is -6. You can see the pattern. So just fill in the blanks. Make sure you got the pattern right, but fill in the blanks, right? So, this is this is +2. All the jumps are +2, right? So it's consistent. And these are all +1. I won't draw them all up, but those are all +1. So it's consistent. We know it's consistent on one side. It's consistent on the other side. We know that we're going to have a linear relation. It's just a question of what is it going to look like. All right, I've got to go to -10 on my y's, and I have to go to only -2 on my x's. So if I go to -10, that means I can make each one of these 1. So I'm just going to 2, 4, 6, 8, and then 10's at the top. And then same thing on the bottom, right? So this is going to be -2, -4, -6, -8. And then -10 is at the very bottom. I didn't write in 1, 3, 5 because I just didn't have room. And then for our x's, we only have to go to -2. So I'm just going to make 4 of these equal to 1. So 1, 2, 3, 4. So this would be -1. 1, 2, 3, 4. This would be -2. And then same thing on the other side. 1, 2, 3, 4. That's +1. 1, 2, 3, 4. That's +2. That's all I need. Okay. All right. Let's put some points on the graph. See where we're at. All right. 1, 2, 3, 4. Okay, good. When x is -2, y is -10. So -2x, -10y, right there at the bottom. -1x, -8. -1, -8. Right there. 0 is -6, so 0 on the x, straight down to -6. 1 is -4, so that's right there. And then 2 is -2, so there's 2 and there's -2. Now it's pretty easy to see that that's a linear relationship, that those are all on a straight line. Okay, but we knew it was a linear relationship because constant change here, constant change there. hopefully that gives you enough information to solve and do the questions in 4.2. If you have any questions or concerns, as always, you let us know. We're happy to help you out.